15 kilometers above your head, right now, a collision is happening that produces one of the strangest particles in the universe. A proton, blasted out of some distant galaxy, traveling at just under the speed of light, slams into a nitrogen nucleus in the upper atmosphere. The collision is violent enough to shatter both particles into a spray of smaller pieces. Among those pieces are pions, unstable, short-lived, gone in a fraction of a microsecond. But before they vanish, they decay. And what they decay into is a muon, quiet, fast, nearly impossible to stop. And according to every straightforward calculation, it should never reach you. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Here is the problem. A muon lives for about 2.2 microseconds before it decays into an electron and a pair of neutrinos. That is it. That is the whole window. Even traveling at nearly the speed of light, 299,000 kilometers per second, a muon should cover roughly 660 meters before it blinks out of existence. The atmosphere it has to cross is 15,000 meters deep. The math is not close. It is not a rounding error. By any classical calculation, fewer than 1 in 10 billion muons should survive long enough to reach the ground. And yet detectors at sea level register thousands of them passing through every square meter of Earth's surface every single minute. Something is wrong. Or rather, something about the universe is profoundly different from what common sense suggests. This is the muon paradox, and it has been sitting in the middle of physics since the 1930s, demanding an explanation that turns out to be one of the most unsettling ideas in the history of science. Before getting into why muons survive, it is worth being clear about what they actually are. A muon is a fundamental particle, not made of quarks, not made of anything smaller that anyone has ever found. It belongs to a family called leptons, the same family as the electron and the tau particle. It carries the same electric charge as an electron, the same spin. In almost every way that matters, it behaves exactly like an electron, except it weighs 207 times more. That extra mass is the strange part. Nobody predicted it. Nobody asked for it. When it was first pulled out of cosmic ray data in 1936, the physicist I.R. Rabi is said to have responded with 3 words. Who ordered that? The question was rhetorical. Nobody had. Nature had just decided to build a heavier copy of the electron and drop it into the universe without an explanation. Right now, as you are reading this or listening to this, muons are moving through you. Not occasionally, constantly. Every minute, several muons pass through your hand if you hold it flat on a table. They pass through the table too, through the floor, down into the bedrock. They lose energy slowly, shedding it through the matter they cross, but they keep going through meters of rock, through the walls of buildings, through lead shielding that would stop almost anything else. They are the most abundant, high-energy charged particles arriving at Earth's surface from space. And they arrive because of something Einstein figured out more than a century ago. Something about the nature of time that still feels like a trick the first time you encounter it. The resolution to the muon paradox is time dilation. Moving clocks run slow. A muon hurtling toward Earth at 0.998 times the speed of light is, from the perspective of a ground observer, aging at a fraction of its normal rate. Its 2.2 microseconds stretch. The particle that should decay in less than a kilometer survives long enough to cross 15 of them. The math works. The detectors confirm it. Every muon that arrives at sea level is a small physical proof that Einstein was right about time being flexible, in a way that still sits uncomfortably against ordinary experience. Muons are not an abstract confirmation of relativity. They are a tangible one. They are here because time bent around their speed. That alone would make the muon one of the more remarkable things in physics. A particle born from a cosmic collision, carrying evidence of special relativity in its very survival. But the muon has not stopped being strange. Physicists have spent decades measuring it with increasing precision, and recently those measurements have started coming back with numbers that do not match what the best theory of matter predicts. Not by a lot, but by enough. And at the level of precision these experiments operate, enough is everything. The standard model of particle physics is the most precisely tested theory in science. It describes every known particle and 3 of the 4 fundamental forces, and it makes predictions accurate to more decimal places than almost anything else in the history of human knowledge. When physicists calculated exactly how the muon should behave in a magnetic field, they got a number. When they measured it in a lab, they got a slightly different one. That difference has not gone away. It has been confirmed by multiple experiments at multiple facilities, and it is pointing at something, some particle, some force, some piece of the universe that the standard model does not include. And the strangest part is not where muons come from, or how many of them are passing through you this second, but what happens when physicists try to measure them precisely. Because that measurement is quietly suggesting that everything we think we know about matter might be missing something. To understand why muons matter, you first have to get comfortable with the fact that nature built the same particle 3 times. The lepton family has 3 members. The electron, which you know, it orbits atomic nuclei, carries electrical current through wires, makes chemistry happen. Then the muon, then the tau. All 3 carry the same electric charge. All 3 have the same spin. All 3 interact with the same forces in the same fundamental ways. If you handed a physicist a list of their properties with the mass removed, she could not tell them apart. They are, in every meaningful sense, the same type of thing. Nature just kept making them heavier. The electron weighs about 0.511 MeV. If you are not used to thinking in megaelectron volts, here is a way to hold that number. An MeV is a unit of energy that physicists use at the particle scale, and when you express particle mass in those units, you are using Einstein's equivalence between mass and energy. The electron's 0.511 MeV is nearly nothing. The muon comes in at 105.7 MeV. That is 207 times heavier than the electron, which sounds abstract until you think about it in terms of what sits around that mass range. A proton, the massive core of a hydrogen atom, weighs in at about 938 MeV. The muon is sitting between these 2 in a strange middle zone, too heavy to behave like an ordinary electron, too light to be anything like a proton. It is not quite one thing and not quite the other. This intermediate position gave physicists serious trouble when they first found it, and we will get to that. But for now, the important thing is that the muon's mass puts it somewhere nature did not obviously need to fill. Here is an analogy that might help. Imagine building materials. You have lightweight balsa wood, which is the electron. You have dense steel, which is the proton. And then someone hands you a block of something that is way too heavy to be balsa, but nowhere near as solid as steel. You did not order this. It does not fit neatly into any shelf in your workshop. That is roughly what physicists felt when the muon showed up. It occupied mass territory that no theory had predicted or required. Now, the muon's charge is -1, identical to the electron's. It carries no color charge, which is the property that makes quarks respond to the strong nuclear force. Because the muon has no color charge, the strong force completely ignores it. This matters because the strong force is, by a wide margin, the most powerful fundamental force in physics. Particles that feel it get dragged into violent interactions with nuclei constantly. Muons sidestep all of that. They interact electromagnetically, and they interact through the weak force. That is it. This combination, heavy enough to sit well above the electron in mass, but unaffected by the strong force, gives muons a distinctive profile that turns out to be extraordinarily useful for physics. As later sections will show, the muon is also, critically, not made of anything. This is worth pausing on. Protons and neutrons are composite objects. They are built from quarks bound together by the strong force. Muons have no internal structure at all. There is no smaller thing inside a muon waiting to be found. It is a fundamental particle, a true point particle with no known size and no constituents. When physicists say a particle is elementary, they mean the question of what it is made of simply does not apply. The muon is one of those. In that sense, it is more like the electron than it is like a proton. They are both irreducible objects, both points in the mathematical description of the universe, and yet their mass difference is a factor of 207. The third member of this family, the tau particle, is heavier still. It comes in at roughly 1,777 MeV, about 17 times heavier than the muon, and nearly twice the mass of a proton. The tau is so heavy, it decays almost immediately, in less than a trillionth of a second, which means it is extremely difficult to study in detail. The muon sits in the middle of this ladder, lighter than the tau, heavier than the electron, long-lived enough to actually travel measurable distances and leave tracks in detectors. This middle position is part of why the muon has ended up being so scientifically productive. Which brings us to the decay. Muons are not stable. Left alone, a muon will fall apart. The mean lifetime is 2.2 microseconds, 2.2 millionths of a second. That sounds brief. In everyday terms, it is essentially nothing. But in particle physics, it is a long time. Many particles decay in nanoseconds, picoseconds, femtoseconds. Some hadrons fall apart so quickly they can only be inferred by their decay products because no detector can catch them directly. The muon, by contrast, hangs around long enough to travel real distances, leave real tracks, and be studied with real instruments. 2 microseconds, at particle physics scales, is almost leisurely. The reason muons live this long comes down to which force mediates their decay. When a muon falls apart, it does so through the weak nuclear force. And the weak force, despite its name being almost understated, is genuinely weak compared to the electromagnetic force, and particularly compared to the strong force. Weak force interactions happen slowly. The probability of a decay event per unit time is low. This is why a free neutron, for instance, also decays through the weak force, and has a mean lifetime of around 15 minutes, which is an eternity by particle physics standards. The muon's 2.2 microseconds reflects the same principle operating at a different mass scale. When a muon decays, it produces 3 particles, an electron and 2 neutrinos, specifically a muon neutrino and an anti-electron neutrino. The W boson, a massive force carrier, briefly mediates the whole process. The muon transforms into a muon neutrino and a virtual W boson, and the W boson then decays into an electron and an anti-electron neutrino. The mass difference between the muon and its decay products is substantial, so a significant amount of energy converts into the kinetic energy of those outgoing particles. Occasionally, in a small fraction of cases, extra particles appear in the final state, an electron-positron pair, or a photon. But the core decay channel is always the same: 1 muon in, 1 electron and 2 neutrinos out. There is something worth sitting with here. Nature took the recipe for the electron. Specific charge, specific spin, no color charge, no substructure, and made a heavier version. Then it made an even heavier version after that. 3 generations of the same fundamental concept, stacked by mass, each one more unstable than the last. Nobody asked for this. No theory demanded it. The standard model accommodates it, describes it, and makes precise predictions about how each generation behaves. But explaining why this pattern exists at all, why 3, why these specific masses, why any repetition, is something the standard model does not do. It accepts the 3 generations as an observed fact and builds from there. This replication goes beyond leptons. The quarks do it too. There are 6 quarks arranged in 3 pairs, each pair heavier than the one before it. The first generation of quarks pairs with the first generation of leptons. The second generation pairs with the muon and the muon neutrino. The third generation pairs with the tau. The whole structure of matter seems to replicate itself twice over, each time at a higher mass scale, each time less stable and more transient. The muon sits in that second generation, the middle copy, heavier than anything we normally interact with, but lighter than the top of the ladder. Nobody has a clean answer for why muons exist as a separate thing from electrons, why nature needed a heavier copy, and that question has been sitting in physics since the 1930s, when someone first pulled one out of a cloud chamber and had absolutely no idea what they were looking at. In 1936, Carl Anderson was already famous. He had found the positron 4 years earlier, and when he looked at the tracks left by cosmic rays in his cloud chamber at Caltech, he saw something that didn't fit any particle he knew. Cloud chambers are elegant instruments. You fill a sealed container with supersaturated vapor, and when a charged particle passes through, it leaves a trail of condensation behind it, like a tiny contrail. The trail curves in a magnetic field. and how much it curves tells you the particle's mass and charge. Anderson knew how electrons curved. He knew how protons curved. He had spent years reading these trails the way a tracker reads footprints in mud. What he was seeing in 1936 did not match either one. The tracks curved too much to be protons. They were definitely not protons, but they curved too little to be electrons. Whatever was leaving these trails through the chamber was something in between, something that had no name yet, something that had no place in any physicist's catalogue of known particles. Anderson and his colleague Seth Neddermeyer ran the measurements again. The answer kept coming back the same. The particle's mass sat somewhere between the electron and the proton, closer to the lighter end but heavier than any fundamental particle anyone had catalogued. They called it the mesotron, from the Greek for middle, because middle was exactly what it was. Not light, not heavy, just wrong. Street and Stevenson confirmed it independently in 1937, with their own cloud chamber results pointing to the same mass range. So this was not a fluke. The mesotron was real. It was out there, raining down from the sky as part of cosmic ray showers, curving through magnetic fields in its stubborn, unexplained way. And almost immediately, someone thought they knew what it was. Here is where the story gets genuinely chaotic. 1 year before Anderson and Neddermeyer published their results, a Japanese physicist named Hideki Yukawa had proposed something. At the time, nuclear physics had a serious open problem. Everyone knew that protons and neutrons were packed together inside atomic nuclei. Everyone also knew that protons carry positive charge, and that positive charges repel each other. The question nobody could answer was why nuclei didn't simply fly apart. Something was holding them together. Some force, stronger than electromagnetism at short range, had to be operating inside the nucleus. Yukawa worked out the mathematics of what a particle carrying that force would need to look like. It would need to be a boson. It would need to have a specific mass range. And when he calculated that mass range, it came out somewhere around 200 times the electron mass. When Anderson's mesotron showed up with a mass around 207 times the electron mass, the match seemed obvious. Too obvious to ignore. Physicists around the world looked at the numbers and reached the same conclusion. Anderson had found Yukawa's particle. The carrier of the strong nuclear force had arrived. This was supposed to be a triumph, the rare case where theory predicted something and experiment delivered it cleanly. For nearly a decade, the mesotron sat comfortably in textbooks as the force carrier Yukawa had predicted, the glue holding atomic nuclei together. The story seemed settled. This agreement between Yukawa's prediction and Anderson's finding looked like textbook physics at its best. For theorists, it was a validation of their mathematical frameworks. For experimentalists, it was confirmation that their measurements meant something profound about nature. Conferences buzzed with the elegance of the solution. The theoretical community embraced the mesotron as Yukawa's particle almost immediately. Physics textbooks were updated. The gap in nuclear physics seemed finally, definitively closed. It felt like one of those rare moments where the universe revealed one of its fundamental secrets. Except the story was completely wrong. The problem surfaced slowly. Physicists started doing careful experiments on what the mesotron actually did when it encountered matter. If this particle carried the strong nuclear force, it should interact vigorously with atomic nuclei. It should get absorbed readily, scatter strongly, leave detectable signatures of those interactions everywhere it went. Instead, it passed through matter almost without noticing. You could put a slab of iron in its path and the mesotron would sail through as if the iron were barely there. This was not what a force carrier of the strong nuclear force should do. A particle whose job was to glue protons and neutrons together should not be ignoring atomic nuclei entirely. The behavior was all wrong. Italian physicist Marcello Conversi and his colleagues ran a crucial set of experiments in Rome in the mid-1940s, during extraordinary circumstances. They were working in occupied Italy, hiding their equipment to avoid confiscation. They found that negative mesotrons stopped in carbon did not get absorbed by nuclei the way they should if they were Yukawa's particles. They just sat there and decayed without triggering the nuclear interactions that the strong force carrier was supposed to produce. The mesotron was ignoring the strong force entirely. It was a lepton, not a hadron. It felt the weak force and electromagnetism, and that was it. Yukawa's particle was still out there somewhere, undiscovered. The actual resolution came in 1947 at the University of Bristol through work led by Cecil Powell. Powell had developed a technique for using photographic emulsion to record cosmic ray tracks, and when his team looked closely at what was happening in the upper atmosphere, they found something Anderson had missed. There were two distinct particles, not one. The first particle came in from space, hit the atmosphere, and quickly decayed into the second particle. Powell's team called the first one the pion, or pi meson. The pion was short-lived, decaying within meters. It interacted strongly with nuclei. It was Yukawa's particle. The second particle, produced when the pion decayed, was the old mesotron, two separate things, masquerading as one for over a decade. The naming situation became a problem almost immediately. The mesotron had been called a mu meson because it belonged to the meson category in the old classification system, but once it became clear that muons were fundamental particles with no internal structure, leptons, like electrons, the word meson became wrong. Mesons, in the emerging quark model of the 1960s and 1970s, were particles built from quarks. Muons were nothing of the sort. They were as fundamental as electrons, just heavier. The term mu meson quietly vanished from technical literature and was replaced with the word muon. A small change in vocabulary, but it reflected a large change in understanding. The discovery timeline, looked at cleanly, is almost embarrassing for physics. A particle found in 1936, misidentified for a decade, properly separated from Yukawa's pion in 1947, correctly classified as a lepton only years after that, and even once the classification was right, nobody had a satisfying explanation for why it existed. The electron existed because atoms needed it. The proton and neutron existed because nuclei needed them. The pion existed because Yukawa's math needed a strong force carrier. The muon did not fit any of these categories. Nature had not been asked for it. No equation had predicted it. No theory required it. It simply showed up in Anderson's cloud chamber and refused to go away. The muon's existence raised uncomfortable questions that particle physics had not learned to ask. Some physicists wondered whether there might be more such particles, equally mysterious and unexplained, waiting undiscovered in the data. The standard model would eventually incorporate the muon as one of the fundamental leptons, but even that classification felt like a filing system rather than a true explanation. It told you where the muon belonged, but not why nature required it. The muon sat there stubbornly real, stubbornly mysterious, stubbornly refusing to fit into any narrative about how nature ought to work. The weight of that strangeness accumulated as the years passed and no explanation emerged. The muon behaved exactly like a heavy electron. Same charge, same spin, same interactions, just heavier and unstable. If you replaced every electron in every atom with a muon, you would get a version of chemistry that mostly worked the same way, scaled down in size, briefly before everything fell apart when the muons decayed. The particle was not exotic in any of the ways that would make it feel necessary. It was simply a copy. A second printing of the electron, made heavier and given an expiration date, for no apparent reason. When Rabi heard about the muon, he reportedly said 3 words that captured what every physicist was feeling. Who ordered that? Right now, without any detector, without any instrument, muons are passing through you. Not occasionally, not in bursts. Continuously, every second of every day, a steady invisible rain of particles is falling through your body, through the floor beneath you, through the rock and soil under that. You cannot feel them, they leave no sensation. But they are there, and they have been falling on this planet since long before anything alive existed to notice. The source of this rain begins far from Earth. Cosmic rays, mostly high-energy protons fired out by supernovae, black holes and other violent events scattered across distant galaxies, travel across enormous stretches of space, and eventually collide with the upper atmosphere. These are not gentle collisions. A single cosmic ray proton can carry more kinetic energy than a professionally thrown baseball compressed into a particle smaller than any instrument can resolve. When it strikes a nitrogen or oxygen nucleus roughly 15 to 20 kilometers above the surface, it does not simply bounce, it detonates. The nucleus breaks apart in a cascade, spraying secondary particles outward in a cone. Among the first things produced in that cascade are pions, short-lived particles that carry the fingerprints of the strong nuclear force. Pions decay almost immediately, within meters, and when they do, the primary product is a muon. Along with a neutrino, a muon emerges from that rapid decay, moving at a significant fraction of the speed of light, pointed roughly toward the ground. This happens constantly, not in isolated incidents, but in a relentless, overlapping stream of events distributed across the entire upper atmosphere. Every square meter of sky above you is a production zone. The numbers that come out of this process are striking. At sea level, roughly 1 muon passes through every square centimeter of the Earth's surface every minute. Scale that up and you get approximately 10,000 muons punching through every square meter per minute. That is not background noise. That is a flood. Muons are the most abundant high-energy charged particles continuously reaching Earth's surface, and they come from no laboratory, no reactor, no human-built machine. The entire planet is bathed in them around the clock. Here is a way to feel the scale of that. Put your hand flat on a table right now. In the time it takes you to read this sentence, dozens of muons have passed through it. Not through the table, through your hand. They entered through the back of your hand, passed through bone and tissue, and continued downward through the wood or stone beneath, through the foundation of the building, and kept going. They did not stop for your hand. They barely noticed it. Consider the biological reality of this. Your body is not impervious to muons. It simply fails to stop them. The muons that traverse your hand do not ask permission. They do not ionize your cells in any way that triggers a cellular response. A muon passes through living tissue the way light passes through glass, and then it is gone. This happens billions of times per day to every organism on Earth. Your cells have adapted to this invisible flux over evolutionary time, not because they recognize it as a threat, but because it has always been ambient radiation, as constant as gravity, as unremarkable in biological terms as the presence of air itself. This penetrating power is not an accident. It comes from what muons are and how they interact with matter. When a charged particle moves through material, it loses energy by interacting with the electrons in the atoms around it. Electrons, being light, shed energy rapidly in a process called Bremsstrahlung. Essentially, a charged particle decelerates in an electromagnetic field and releases that lost energy as radiation. Electrons are so light that they decelerate sharply and release that radiation constantly, which is why electrons are stopped by relatively thin shielding. Muons are 207 times heavier than electrons. That greater mass means they decelerate far more slowly in the same electromagnetic fields. The Bremsstrahlung losses are dramatically reduced. A muon plowing through dense rock loses energy gradually rather than all at once, which means it can travel through hundreds of meters of solid stone before finally stopping. The same mass that made muons strange and hard to classify when Anderson first spotted them in his cloud chamber is the property that makes them nearly unstoppable once they are moving. This penetrating capability has consequences everywhere. Muons reach the deepest mines on Earth. They pass through the hulls of submarines. They move through the foundations of large buildings as if those structures are barely there. If you are standing on a mountain at 4,000 meters, the muon flux reaching you is noticeably higher than it is at sea level, because there is simply less atmosphere above you to absorb the cascade. Roughly half the atmosphere's muon stopping power is in the lower few kilometers. Climb above that and you are exposed to a larger fraction of what the upper atmosphere produces. Pilots and crew on commercial flights, cruising at 10,000 meters or higher, receive muon flux rates several times what people on the ground experience. It is not dangerous at those exposure levels, but it is measurable, and regulators in some countries track cumulative radiation exposure for flight crews partly because of it. The process that generates all of this is running without pause. Every hour, every day, cosmic rays from distant parts of the galaxy are hitting the atmosphere, creating cascades, producing pions, producing muons, sending them downward. The shower is global. It does not discriminate between ocean and land, between inhabited and uninhabited ground. Somewhere above Antarctica right now, a cascade is unfolding. The same thing is happening above the Pacific, above the Sahara, above every city. The muon rain is uniform, ancient, and relentless. What is remarkable is that none of this should work. The numbers that describe muon production are straightforward. The numbers that describe muon decay are also straightforward. The problem is that when you put them together honestly, they do not add up. A muon has a mean lifetime of 2.2 microseconds. That is how long it survives, on average, before decaying into an electron and two neutrinos. At the speeds muons travel, which approach 99.8% of the speed of light, you can calculate how far a typical muon should get before it decays. The answer is somewhere around 660 meters. The upper atmosphere where muons are produced sits 15,000 meters above the ground. There is no version of simple arithmetic that gets a particle with a 660 meter range from 15 kilometers up to a detector at sea level. Most muons should vanish high in the atmosphere, long before they come anywhere near the surface. The detectors on the ground should be registering almost nothing. Instead, they register thousands of muons per minute. The discrepancy is not a rounding error. It is not a measurement artifact. It is enormous, orders of magnitude beyond what classical physics allows. When physicists in the early 20th century first started mapping the muon flux carefully at different altitudes, this contradiction sat right in front of them with no easy resolution. They knew the lifetime, they knew the speed, they knew the altitude of production. The math was simple, the math was wrong. But here is the problem that stumped physicists when they first tried to work out where all these muons were coming from, because by any straightforward calculation, they should not be here at all. Here is the calculation that should have made muons impossible. Muons are born in the upper atmosphere, roughly 15 kilometers above the ground. They get there because cosmic ray protons slam into atmospheric nuclei at altitude and trigger a cascade. Pions first, then those pions decay into muons within meters. The muons inherit the velocity of that cascade. They are moving at approximately 0.998 times the speed of light, which is about 299,500 kilometers per second. That is fast. That is almost incomprehensibly fast. And it still is not enough, because here is the number that breaks everything: 2.2 microseconds. That is the mean lifetime of a muon. 2.2 millionths of a second. After that window closes, a muon decays into an electron and two neutrinos and ceases to exist. So take the speed, 0.998 c, essentially the speed of light, and multiply it by the lifetime. Speed of light is roughly 300,000 kilometers per second, or 300 meters per microsecond. 2.2 microseconds at that speed gives you about 660 meters. That is how far a muon should travel before it decays. Not 15 kilometers, not even close. 660 meters. The atmosphere is more than 20 times that distance. The number isn't slightly off. It is wrong by an order of magnitude, before you even account for the fact that muons don't all live exactly 2.2 microseconds. That's a statistical average, and many muons die much sooner. Run the actual probability distribution and the situation gets worse. The fraction of muons that should survive the full 15-kilometer descent without decaying, based purely on classical physics, is not 1 in 100. It is not 1 in a million. It comes out to something in the range of 1 in 10 billion, depending on the energy of the muon and the exact altitude of production. 1 in 10 billion. And yet detectors at sea level pick up thousands of muons every single minute per square meter of surface. Not a handful, not a statistical trickle. Thousands, every minute, continuously. Something is catastrophically wrong with the calculation. When physicists first started getting a clear picture of this problem in the late 1930s and early 1940s, the discrepancy didn't look like a rounding error or a bad measurement. It looked like a fundamental breakdown. You had a particle with a known decay rate. You had a known distance it needed to travel. The math was elementary. Distance equals rate times time. Any student could do it. The answer said the muons shouldn't be there, but they were there, unmistakably, registering in detector after detector at sea level, showing up in cloud chambers, triggering Geiger counters. The universe was producing the wrong answer. To appreciate how strange this is, think about it from a different angle. Imagine you released 1,000 muons at the top of a 15-kilometer column. By the time that column ran out, classical physics says essentially all of them should be gone. Not most, not the slow ones. All of them, with almost nothing left. The survival fraction is so small, it is effectively zero. The numbers don't allow for an argument about statistical outliers or unusually long-lived individual muons. The gap between prediction and observation is not sitting at the edge of a confidence interval. It is orders of magnitude off, which in physics is not a measurement problem. It is a sign that something is wrong with the framework producing the prediction. This is what made the muon problem genuinely unsettling for early researchers. The physics being used was not exotic. It was basic kinematics, the kind of calculation physicists had trusted for decades. And it was giving an answer that was completely, empirically wrong. You could go outside with a detector and disprove it yourself. Every muon hitting that detector was a data point contradicting the math. Some physicists initially suspected the measurements were off. Maybe the altitude of production was being underestimated. Maybe the muon lifetime figure needed revision. Those hypotheses got tested and eliminated. The production altitude was real, confirmed through multiple methods. The lifetime was real, measured in controlled lab settings with muons at rest. The numbers going into the calculation were correct. The calculation itself was the problem, or rather, the physics underlying the calculation was wrong, in a very specific and non-obvious way. The problem demanded immediate and serious attention. This was not merely a theoretical puzzle. Muons were hitting Earth's surface in measurable quantities that could not be dismissed or explained away. Every particle detector built in that era confirmed it. The data accumulated relentlessly. The discrepancy would not shrink with better equipment or more careful measurement. Physicists faced an uncomfortable reality. Either the universe violated their mathematical framework, or that framework was incomplete in some fundamental way. Neither conclusion was reassuring. Both suggested that something crucial about how reality actually worked remained hidden from view. There was a second angle that made this worse. Consider the energy budget. Muons are moving at 0.998 c. At those speeds, they carry significant kinetic energy. You might try to argue that high-energy particles somehow live longer, that energy affects decay rates in some classical way. But that is not how decay works under standard physics. The decay rate is set by the particle's properties, not by how fast it is moving relative to a detector. A muon is a muon. It decays when its internal clock runs out. The clock runs at a fixed rate. The distance it covers before the clock runs out is just speed multiplied by time, and the time doesn't change because of the speed. That is the assumption embedded in classical physics. Distance, speed, time, fixed relationships, predictable, certain. Nature disagreed. What the data was quietly demanding, before anyone had the framework to say it clearly, was that the relationship between time and motion was not fixed the way everyone assumed. Something was stretching. Something was making these muons last longer than their decay rate permitted, or making the distance shorter than the geometry of the atmosphere suggested, or both. The classical framework had no room for either option. In that framework, a microsecond is a microsecond for everyone everywhere. A meter is a meter, and the calculation stands. Except the calculation was wrong, and the muons were there. This is not a paradox in the loose sense, the kind where something seems contradictory, but resolves cleanly once you think carefully enough. This is a genuine contradiction between a mathematical prediction and a measured physical reality, with no exit available inside the rules of classical mechanics. The numbers do not work out. They cannot be made to work out by adjusting constants or refining measurements. The framework that produces the contradiction has to be replaced. The only way out of this contradiction, the only framework that makes the numbers work, requires accepting something about time that still feels wrong even after you understand it. Einstein's special relativity makes one initial demand that sounds reasonable and has consequences that are almost impossible to fully accept. The speed of light is the same for every observer, no matter how fast they are moving. That's it. That's the starting point. Light travels at roughly 300 million meters per second, and it doesn't matter if you're standing still, flying at half the speed of light, or falling into a black hole. Every observer measures the same value. No adjustments, no relative corrections. The speed of light is a fixed constant nailed into the fabric of the universe itself. That sounds almost boring when you first hear it. It isn't. The problem comes when you start following the logic. If the speed of light is constant for everyone, and speed is defined as distance divided by time, then distance and time themselves have to bend to keep that number locked. There is no other way to make the mathematics consistent. If two observers moving relative to each other both measure light at the same speed, they cannot be measuring the same distances and the same time intervals. Something has to give. What gives is time. What also gives is space. And this is where the consequences start becoming deeply strange. Time dilation is the first consequence. A clock that is moving relative to you runs slow, not because of mechanical interference, not because of vibration or electromagnetic noise. It runs slow because that is what time actually does when matter moves through space. The effect is real, physical, and measurable. The faster the clock moves relative to you, the slower it ticks. At everyday speeds, cars, planes, even rockets, the effect exists, but is so small that precision atomic clocks are needed to detect it. As you approach the speed of light, the effect becomes enormous. At 0.998 times the speed of light, the time dilation factor is roughly 15. A clock moving at that speed ticks once for every 15 ticks of a stationary clock beside you. Now bring the muon back into this. A muon is born roughly 15 kilometers above the surface when a pion decays in the upper atmosphere. It travels downward at approximately 0.998 times the speed of light. In its own reference frame, the frame where the muon is at rest, it has a mean lifetime of 2.2 microseconds. That is the number the muon experiences. By classical physics, even moving at the speed of light, 2.2 microseconds gets you about 660 meters. The atmosphere is 15,000 meters deep. The numbers don't work. The muon should be gone long before it arrives. But the muon is not moving at an everyday speed. It is moving at 0.998 c. The time dilation factor at that velocity is about 15, which means that while the muon experiences 2.2 microseconds of its own time ticking by, a ground-based observer watching that muon travel downward measures its lifetime as something closer to 33 microseconds. 33 microseconds at 0.998 times the speed of light. That gets you roughly 10 kilometers. The numbers work. Just barely, accounting for the spread in energies across the actual population of muons reaching the surface, but they work. The survival of muons at sea level is not a mystery anymore once you allow time to run at different rates for different observers. Here is where most explanations stop. But there's a second half to this that is equally important, and it comes from asking a different question. From the muon's perspective, what is happening? The muon is not experiencing time dilation. In its own rest frame, it is stationary. It exists for 2.2 microseconds, and then it decays. That is its life. So how does it travel 15 kilometers in 2.2 microseconds? From the muon's point of view, the answer is that it doesn't. The atmosphere isn't 15 kilometers thick. It's contracted. Length contraction is the flip side of time dilation, and it is just as real. When an object moves relative to you, distances along the direction of motion shrink. The faster the object moves, the shorter those distances become. From the muon's reference frame, the entire column of atmosphere between its birthplace and the surface is contracted by that same factor of 15. 15 kilometers becomes approximately 1 kilometer. The muon covers about 1 kilometer in 2.2 microseconds at near light speed, without any problem at all. No extended lifetime required. No paradox. The distance simply isn't as long as it looks from the ground. There is an important detail embedded here that makes the consistency even more remarkable. The ground observer and the muon observer cannot both be measuring the same thing in the same way, yet they arrive at the same physical result. The muon survives and reaches the detector. This is not a coincidence, and it is not a failure of logic. It is a feature of how space-time actually works. The contraction factor and the dilation factor are mathematically linked. They are two sides of the same transformation. When you work through the algebra carefully, you find that the contracted distance and the dilated time produce the same velocity. The muon's speed in its own frame, 0, combined with the contracted distance and the dilated time, produce the same velocity. The muon's speed in its own frame, 0, combined with the contracted distance, gives the same arrival time at the surface as the ground frame calculation. This is what it means for the laws of physics to be universal. They don't require different observers to agree on space and time separately. They only require that those observers agree on what actually happens. Both of these descriptions, the ground observer's dilated lifetime and the muon's contracted atmosphere, are equally valid. Neither one is more correct than the other. They are two different accounts of the same physical event, each valid within its own reference frame, and both accounts produce the same result. The muon arrives at the surface. Special relativity is not claiming that one observer is right and the other is wrong. It is saying that time and space are not absolute, and two observers moving relative to each other will measure different values for both without either one making an error. The universe holds the outcome constant while allowing the bookkeeping to vary. This is genuinely difficult to sit with. It is not the kind of thing that clicks into place through a single analogy. Physicists who have worked with relativity for decades still describe a residual strangeness when they think carefully about what it means. Time running at different rates for different observers isn't a quirk of perception. It's not a measurement artifact. It is the actual structure of reality. For a long time, all of this was theoretical. Beautiful mathematics, consistent logic, radical implications. But physics ultimately demands experimental verification. Predictions are not enough. Someone had to measure this. In 1941, Bruno Rossi and David Hall did exactly that. They set up muon detectors at two different altitudes. One detector was placed on Mount Washington in New Hampshire at roughly 1,900 meters above sea level. The other was placed at sea level. The question was simple. How many muons reached the top of the mountain per unit time? How many reached the bottom? The ratio of those two numbers, combined with the travel time between the two altitudes, would tell you whether muon lifetimes were being extended in the way special relativity predicted. If there were no time dilation, the muon flux at sea level should be dramatically lower than at the mountaintop. Most muons should decay during the descent. The expected fraction surviving without relativistic effects was small. With time dilation, the fraction should be much larger, roughly consistent with a lifetime extended by the relativistic factor appropriate for muon speeds. Rossi and Hall measured the flux at both locations. The ratio matched the prediction from special relativity, not approximately. It matched. This was one of the first direct experimental confirmations of time dilation using actual physical particles. Not clocks, not thought experiments. Real particles produced by cosmic rays, counted at two altitudes, whose survival rate could only be explained by time passing at different rates depending on how fast the particles were moving. The experiment has been repeated many times since, with increasing precision, and the result has never wavered. Each repetition, each refinement of the measurement, each new technology applied to the same question has only strengthened the confirmation. The data are overwhelming and consistent. There is no ambiguity in what the muons are telling us. Something worth holding here. The Rossi-Hall experiment didn't confirm a theoretical curiosity. It confirmed that the universe operates according to rules that are genuinely alien to everyday intuition. Time is not a river flowing at a fixed rate through the cosmos. It is more like a material that stretches and compresses depending on motion. The muon makes this concrete. Every time a detector registers a muon at sea level that physics says shouldn't have survived, it is not a glitch or an anomaly. It is relativity, working exactly as Einstein described, made visible in particle counts. What makes muons particularly powerful as a demonstration of this is that they aren't exotic laboratory creations. They arrive constantly, produced by processes happening 15 kilometers above every point on Earth, every second of every day. The cosmic ray flux that generates them has been continuous for billions of years. This means that for as long as Earth has had an atmosphere, time dilation has been happening above it, quietly, at enormous scale, with muons as the evidence. Einstein hadn't been born yet. The effect did not wait for him. There's a version of this that makes the whole thing feel almost mocking in its simplicity. You don't need a particle accelerator to see time dilation. You need a mountain and a particle detector. The universe has been running this demonstration continuously since before life existed on the planet's surface that the muons are falling through. The lesson was always there. It just required someone willing to question whether time was really as fixed as it felt. Every muon that registers in a detector at sea level is carrying a message from the universe about the nature of time. And the message is that time is not the fixed backdrop you experience it as, but something that bends around the speed of matter moving through space. If you want to test whether time really slows down for fast-moving particles, the cleanest way is to catch some of those particles and make them go in circles. That sounds almost too simple, but in practice, it is one of the most elegant experimental designs in the history of physics, because a circular path solves a problem that straight-line measurements cannot. If a muon is traveling in a straight line, it passes through your detector once and disappears. You can count how many arrive, compare to how many you expected, and infer something about time dilation. But the inference always carries uncertainty. What you really want is to watch the same muon for as long as possible and clock it directly. A storage ring does exactly that. The basic idea is to inject muons into a large circular magnetic field. The field bends the muon's path continuously, curving it into an orbit so that instead of flying off in a straight line and vanishing, the muon circulates. It goes around and around the ring, and the detectors surrounding it can track it, read its decay products as they appear, and measure how long the muon actually survived. You are not inferring anything. You are watching the clock run in real time. At CERN, physicists built exactly this kind of machine. The muon storage ring there was 14 meters across, not 14 kilometers. 14 meters. A ring you could fit inside a large lecture hall. Muons were injected at an energy of 3.1 GeV, which is moving at a serious fraction of the speed of light. At that energy, the relativistic factor, the gamma value that determines how much time slows, worked out to roughly 29. That number is what the equations predict for a muon at that speed, and it carries a very specific consequence. A muon at rest decays in an average of 2.198 microseconds. A muon, moving at the velocity inside that ring, by the predictions of special relativity, should survive approximately 29 times longer as measured by a clock sitting still in the laboratory. That works out to a dilated lifetime of around 64.435 microseconds. That is the prediction. Now here is what made this experiment remarkable. The physicists measured it. They measured it to a precision of 0.1%, and the number they got matched. Not approximately, not within the right order of magnitude. It matched to within 1 part in 1,000, which in experimental physics is extraordinary. The muon's clock was genuinely running slow, by exactly the factor Einstein's equations said it should. The key paper came from Bailey and colleagues in 1977. What they did went further than simply confirming time dilation again. Their experiment was set up in a way that directly confronted something called the twin paradox, which is one of those ideas in special relativity that sounds like a logical contradiction the first time you hear it. The twin paradox goes like this. Imagine two identical clocks sitting side by side. One stays in the lab, the other gets sent away at high speed and then comes back. When the traveling clock returns, it shows less time has passed than the stationary clock. The moving clock aged more slowly. That is time dilation. But here is the apparent paradox. From the perspective of the moving clock, it was the stationary clock that was moving away and coming back. So shouldn't the stationary clock be the one that aged more slowly? The paradox seems to make the situation symmetrical in a way that leads to a contradiction. The resolution is that the situations are not actually symmetrical. The traveling clock had to accelerate to turn around and come back. The stationary clock never did. The asymmetry in acceleration breaks the symmetry in the problem, and the traveling clock really does age less. There is no contradiction, but it took physicists some time to feel fully comfortable with that answer. Muons in a storage ring are a direct physical test of this. The muon leaves the injection point, curves around the ring, comes back past the same detectors, curves around again, and keeps going. The lab frame clock sits still. The muon's clock, the internal process that governs its decay, runs slow. When the muon finally decays, It has survived far longer than a muon sitting at rest would have. The muon went away in circles, just like the twin in the paradox, and came back with its clock behind. Bailey's experiment confirmed this with precision that left no room for doubt. There is another result buried in that experiment that deserves more attention than it usually gets. The muons in the ring were not just moving fast, they were also accelerating. Circular motion is acceleration. The muon's direction was constantly changing, which means a constant centripetal force was acting on it the whole time. Some early versions of the twin paradox resolution lean heavily on acceleration as the key factor. If acceleration were directly causing the time difference, you would expect the transverse acceleration in the ring to influence the muon's decay rate. But it did not even slightly. The decay rate matched the prediction based purely on velocity, with zero measurable contribution from the centripetal acceleration. This was a clean, unambiguous result. It was the speed that mattered, not the acceleration. Special relativity said exactly that, and the muons confirmed it. What this meant for physicists was not just philosophical reassurance, it was a practical result with engineering consequences. If acceleration affected time dilation, then designing particle accelerators would involve an entirely different set of corrections. The fact that it doesn't simplifies things. The factor you need to account for depends on speed, and speed is something you can calculate precisely, because that accounting is not optional. Once you are running particles at the energies involved in modern accelerators, time dilation is not a small correction you can ignore. It changes the numbers significantly. A muon stored at 3.1 GeV lives 29 times longer than at rest. Push the energy higher and the factor scales with it. At the energies of experiments at CERN today, the dilation factors can be in the hundreds or thousands. The particles you are trying to study would simply decay before they reached your detector, if you didn't know exactly how their lifetime stretches with speed. Every beam optics calculation, every detector timing window, every decay length estimate, all of it depends on time dilation being exactly what special relativity predicts it to be. It is worth sitting with what the storage ring experiments actually demonstrated. Before them, time dilation was a confirmed prediction, but one that some physicists still thought of as a theoretical consequence, rather than a measurable physical reality. The atmospheric muon experiments had shown the effect in a broad, statistical sense, but the storage ring experiments measured it precisely, on a controlled population of particles, in a laboratory where every variable was tracked. There was no longer any serious way to argue that time dilation was an artifact of measurement or a statistical illusion. It was real, it was quantified, and it matched Einstein's equations to 4 significant figures. That is an unusual level of precision for a philosophical claim to achieve. Most arguments about the nature of time stay in the realm of interpretation. This one came back with a number. The number was 64.435 microseconds. The prediction was 64.435 microseconds. And the universe did not flinch. The muon storage ring experiments are not curiosities. Modern particle accelerators run at energies where relativistic time dilation changes particle lifetimes by factors of thousands. And every experiment at CERN or Fermilab accounts for this in its calculations as a matter of routine. Because muons pass through almost everything, someone eventually realized they could be used to look inside things that had no other way of being examined. The logic is clean once you see it. X-rays work because different materials absorb radiation at different rates. Bone stops more than soft tissue. Dense metal stops more than bone. You point a beam of radiation at an object, put a detector on the other side, and read the shadow. That approach fails completely when the object is a pyramid or a volcano. The material is too thick and too dense for any conventional beam to penetrate. But muons are already doing the penetrating. They fall through rock, through concrete, through hundreds of meters of stone, and they do it constantly, without any machine generating them. You don't aim them, you don't produce them, you just catch the ones that make it through. This technique has a name, Muon Tomography. The principle is that denser material absorbs and deflects muons more than empty space or lighter material does. If there is a void hidden inside a mountain of stone, more muons will arrive at a detector placed on the far side of that void than from directions where solid rock blocks the path. The distribution of muons reaching the detector is not uniform. It maps the internal structure of whatever the muons pass through. By recording which directions sent more muons and which sent fewer, researchers can reconstruct a three-dimensional picture of what is inside. The Egyptian pyramids were an obvious target. They are enormous. They were built by a civilization that kept secrets intentionally, and they have been studied for centuries without anyone fully mapping what is inside them. Conventional methods can probe surface cracks, peer through small openings, or send in cameras on cables. None of that tells you what is behind a wall of solid limestone several meters thick. Physicists had actually attempted muon imaging of the pyramids as early as the 1960s, when Luis Alvarez, a Nobel Prize-winning physicist, ran detectors inside the Khafra pyramid looking for hidden chambers. That experiment found nothing. The technology at the time was limited. In 2017, a project called Scan Pyramids changed what was possible. An international research team placed muon detectors both inside and outside the Great Pyramid of Giza. They ran the experiment for months, accumulating enormous numbers of muon tracks. When they analyzed the data, something emerged that nobody had seen before. A large void, roughly 30 meters long, sitting above the Grand Gallery in the interior of the structure. It had been there for 4,500 years. No excavation had found it. No historical record mentioned it. Muons found it without disturbing a single stone. The discovery triggered immediate debate about what the void actually was. A construction gap? A relieving chamber? A passage that was sealed and forgotten? The point is not that muon imaging answered every question. It is that it asked a question nobody could ask before. It revealed a shape in the dark that archaeology had no other tool to detect. The Great Pyramid Void is now one of the most studied architectural mysteries of the ancient world, and it exists as a mystery only because particles from distant galaxies happen to fall through it at the right angle for a few months of detector time. Volcanoes presented a different kind of problem. The interior of an active volcano, the plumbing system of magma chambers, channels and dense plugs of cooled lava, changes over time and has direct consequences for eruption prediction. Geologists have seismic tools and gas sensors, but getting a direct image of where the dense material is and where the empty passages are requires something that can actually penetrate the bulk of the mountain. Muon imaging has been applied to multiple active volcanoes, including Etna in Italy, Asama in Japan, and Puy de Dôme in France. The detectors sit on the volcano's flank, or at its base, and the muon flux from the direction of the summit tells researchers how much dense material the particles crossed. Over months of observation, if the dense plug near the summit grows or shifts, the muon flux changes. The image updates. You are watching the inside of a volcano breathe. Then there is an entirely different use case. Less romantic, but arguably more urgent. Nuclear materials are dense. Uranium and plutonium are among the heaviest elements on Earth, and they scatter muons in distinctive ways that lighter materials do not replicate. Conventional cargo scanning at ports and border crossings uses X-rays, but X-rays can be blocked by shielding materials that are not themselves suspicious. Lead stops X-rays. Muons go through lead. If someone wanted to move a significant quantity of highly enriched uranium inside a lead-lined container through a cargo checkpoint, conventional scanners would see a bright shadow and not much else. Muon detectors placed above and below a cargo container can record scattering angles. A lead container with nothing inside produces one S key, attering pattern. A lead container with something dense and high atomic number inside produces a different one. The muon carries information about what deflected it, and that information is not easy to hide from. Research groups and national laboratories have been developing muon-based cargo screening systems for years. The challenge is time. At sea level, you get roughly 10,000 muons per square meter per minute, which sounds like a lot until you realize that imaging a cargo container to sufficient resolution requires accumulating enough tracks to produce a statistically clear picture. That takes minutes. Port operations measure things in seconds. The technology is real, but the throughput problem is still being worked on. It is an engineering challenge, not a physics challenge. Medical research has explored muons from a different angle entirely. Because muons penetrate deeply and deposit energy in a narrow range at the end of their path, similar in some ways to the Bragg peak behavior used in proton therapy for tumors, there has been interest in whether muons could be directed at tumors buried in tissue too deep for other forms of radiation therapy to target precisely. This requires producing muons artificially rather than harvesting cosmic ones, which means particle accelerators and significant infrastructure. The research is real. Clinical muon therapy was actually explored at particle facilities in the 1970s and 1980s, with mixed results. The field has not become mainstream, but the underlying physics is sound. A muon deposits its energy in a controlled location, inside the body, in a way that an X-ray or a conventional gamma ray does not. What ties all of these applications together is something worth pausing on. The cosmic muon flux costs nothing to produce. It requires no reactor, no accelerator, no power plant. It falls from the sky in numbers large enough to image ancient stone monuments and active mountains and metal shipping containers. And it has been doing so continuously for billions of years. Every application in this field, the pyramid scans, the volcano monitors, the cargo scanners, requires only detectors. The particles themselves are provided for free by the universe. Physicists spent decades treating muons as a nuisance in underground experiments, something to be shielded against, noise to be filtered out. At some point, someone inverted the question. What if the noise was the signal? All of this, from pyramid voids to volcano interiors, runs on the same cosmic radiation that has been falling on Earth since long before humans existed. Muons produced in the upper atmosphere by particles from distant galaxies, repurposed as a free scientific instrument. The standard model of particle physics is the closest thing science has to a complete theory of matter. It describes every known particle and 3 of the 4 fundamental forces, and it makes predictions accurate to more decimal places than almost any other scientific theory in existence. That is not an exaggeration. The standard model has been tested against reality in thousands of experiments across decades, and it keeps winning. It describes how quarks combine into protons and neutrons. It describes the electron, the photon, the neutrino. It predicts how particles should behave when they collide, how they decay, what forces pull on them and how hard. The electromagnetic force is in there. The weak nuclear force is in there. The strong force that holds atomic nuclei together is in there. Gravity is the one thing it doesn't cover, and that omission is a separate problem, a famous one, but for almost everything physicists study in a laboratory. The standard model is the map, and for decades, the map matched the territory with almost uncanny precision. Here is what makes it strange. This framework that describes the building blocks of everything was assembled piece by piece, mostly in the second half of the 20th century, by large numbers of physicists working across different experiments, different countries, different theoretical traditions. It wasn't handed down whole, it was stitched together. And despite that, it produces numbers that match experiment at the level of 1 part in a billion, not 1 in 1,000. 1 in a billion. That kind of agreement between theory and measurement is almost unsettling. So when a number comes back wrong, physicists notice. To understand where the muon fits into this, you need to understand something about spin. Every fundamental particle carries a property called spin. It's not spin in the way a top spins. Nothing is literally rotating, but the math that describes it looks like rotation, and it produces real measurable effects. One of those effects is magnetic. A charged particle with spin behaves like a tiny magnet. It has a north pole and a south pole, in a sense, and it responds to external magnetic fields the way a compass needle responds to Earth's field. The strength of this magnetic effect is called the magnetic moment. The bigger the magnetic moment, the stronger the particle responds to a magnetic field around it. For a simple spinning charged particle, you'd expect the magnetic moment to take a specific value. If you just do the classical calculation, you get a number called g equal to 2, exactly 2, a clean result. But quantum mechanics doesn't let things stay clean. In quantum field theory, a charged particle moving through space is never really alone. It's constantly surrounded by a churning sea of virtual particles, pairs of particles and antiparticles that flicker in and out of existence in tiny fractions of a second, barely real by any ordinary measure. but real enough to affect how the particle behaves. These virtual particles tug on the muon's magnetic moment. They shift it away from exactly 2. The deviation is small, but it's precise, calculable, and real. This deviation has a name. Physicists call it the anomalous magnetic moment. They measure it as the quantity g minus 2 divided by 2. Written out, it's just a small number, close to 0. But that small number carries an enormous amount of information about what kinds of particles and forces exist in the universe, because every species of particle that can interact with the muon, even virtually, leaves a fingerprint on that number. This is where the Standard Model earns its reputation. The calculation of the muon's anomalous magnetic moment requires accounting for every known particle in the Standard Model that could appear as a virtual participant in those quantum fluctuations. Electrons, quarks, photons, W bosons, Z bosons, gluons, the Higgs boson. Every single one contributes some tiny amount. Physicists have spent decades computing these contributions, and the calculations run to hundreds of pages of algebra. The final predicted value sits at roughly 0.001, 1659, 1810. That sequence of digits represents some of the most demanding theoretical work in the history of physics. Now here is something worth sitting with for a moment. Suppose something exists in the universe that isn't in the Standard Model. Some new particle, undiscovered, not yet detected in any collider. If that particle can interact with the muon, even briefly, even virtually, it will shift the anomalous magnetic moment away from the Standard Model prediction. The muon won't know what it interacted with. Neither will you, but the number will be different. And if you measure the number precisely enough, you'll see the discrepancy. This is the reason the muon's anomalous magnetic moment is sometimes called a window into unknown physics. It's not just a test of what we know, it's a probe pointed at what we don't. The electron has an anomalous magnetic moment too, and it's been measured with extraordinary precision, arguably the best measured quantity in all of physics. But the electron is light. It's the lightest charged particle, and lighter particles are less sensitive to the effects of very heavy unknown particles. Because the heavier the virtual particle, the smaller its contribution to the magnetic moment. The muon, being 207 times heavier than the electron, couples more strongly to whatever heavy unknown things might exist at higher energies. It's more sensitive to new physics by a factor that physicists find genuinely useful. If something heavy and unknown is lurking out there, the muon is more likely to feel it than the electron is. This is not a small distinction. It's the reason physicists have been measuring the muon's anomalous magnetic moment rather than just settling for the electron's version. Think of it this way. If you're trying to detect the faint gravity of a distant object, a heavier pendulum bob will respond more noticeably than a lighter one. The muon is the heavier pendulum. It swings more, and if something invisible is pushing it, the swing goes off. The theoretical prediction for the muon's anomalous magnetic moment sits in a peculiar position in physics. It's precise enough that any new particle heavier than a few hundred GeV that interacts with muons would shift the value detectably. That covers a huge range of candidates. Supersymmetric particles, if they exist, interact with muons. Extensions of the Higgs sector, if they exist, do too. Dark photons, leptoquarks, new force carriers that nobody's seen yet. All of them would nudge the anomalous magnetic moment in some direction, by some amount that the calculation would, in principle, reveal. The Standard Model number is a baseline. Measure the real number. Compare. The difference, if there is one, is a clue. This is the kind of measurement that gets theorists and experimentalists into the same room arguing. It's rare that a single quantity carries this much information. Most physical measurements tell you something specific about one process, one interaction, one energy scale. The anomalous magnetic moment of the muon is almost uniquely sensitive to the entire landscape of what might exist at high energies, encoded into a single dimensionless number. For decades, measuring it more precisely has been recognized as one of the most productive things physics could do, because even a tiny deviation from the Standard Model prediction would carry real weight. The muon's anomalous magnetic moment is one of those predictions, calculated to 10 significant figures, and when physicists actually measured it in a lab, the number came back wrong. The experiment that might be breaking physics doesn't look like much from the outside, a circular ring of magnets about 14 meters across, sitting in a specially built building at Fermilab in Illinois. Walk past it and you might mistake it for industrial equipment. A large torus of superconducting magnets, carefully shielded, cooled to temperatures colder than deep space, humming with a magnetic field so uniform that physicists spent years tuning it to a precision of a few parts per million. It does not announce itself, but what happens inside that ring is one of the most delicate measurements in the history of science, and the number it keeps returning is making theorists deeply uncomfortable. To understand what the experiment is actually doing, you need a picture of how a muon behaves in a magnetic field. A muon has spin. It behaves like a tiny magnet with an axis, and when you place it inside a magnetic field, that axis doesn't stay fixed, it precesses, wobbles, like a gyroscope slowly tipping around its rotation axis. The rate of that wobble is set by the muon's magnetic properties, and the standard model predicts exactly what that rate should be. Measure the wobble rate, compare it to the prediction, and you have a test of whether the standard model is complete. That is the entire experiment, stripped down to its core. Inject muons, watch them spin, measure the wobble. The story starts not at Fermilab, but at Brookhaven National Laboratory on Long Island, New York, in the late 1990s. The Brookhaven Muon G2 experiment was the first attempt to push this measurement to a precision that could actually challenge the standard model. The setup used a storage ring 14 meters in diameter, the same ring that sits in Illinois today. Muons were injected at 3.1 GeV into the ring and kept circling by the magnetic field. As they circled, their spins precessed. Detectors lining the ring recorded the decay electrons streaming outward as muons eventually broke down, and the timing of those electrons encoded the precession rate. It took years of data collection, years of painstaking calibration of the magnetic field, years of ruling out systematic errors. When the Brookhaven team published their final result in 2004, the precession rate came back slightly higher than the standard model predicted, not dramatically higher. The discrepancy was measured in fractions of a part per million, but it was real, and it persisted across multiple runs of the experiment, and the statistical significance was enough that it could not simply be waved away. The anomaly had a name almost immediately. Physicists called it the Muon G2 anomaly, shorthand for the anomalous magnetic moment of the muon, and it lodged itself in the back of the field's mind like a splinter. Were they seeing new physics, or a mistake? The Brookhaven results sat at roughly 3.7 standard deviations from the standard model prediction. In particle physics, 5 sigma is the threshold for a discovery claim. At 3.7, you were in uncomfortable territory, too significant to ignore, not significant enough to declare victory. The field needed a better experiment, more data, higher precision. Here is where the story takes a turn that belongs in a different kind of documentary entirely. The Brookhaven storage ring, that 50-foot wide ring of superconducting magnets, needed to move to Fermilab in Illinois, where a more powerful muon beam could feed it with far higher statistics. The problem was that the ring could not be disassembled. The superconducting coils inside were wound in such a way that cutting them apart and reassembling them would destroy the precision that had taken years to achieve. The whole ring had to travel intact. In 2013, they moved it. The ring was loaded onto a barge, floated out of Long Island Sound, carried by sea around the coast of Florida, up the Mississippi River, and then hauled overland on a specially designed flatbed truck through the streets of Illinois in the middle of the night. The journey took 5 weeks and covered nearly 3,200 miles. Local police escorts, trimmed trees, careful planning around low-hanging power lines. The ring arrived at Fermilab without damage. It was one of the stranger logistics operations in physics history, and it worked. Fermilab's Muon G2 experiment began collecting data in 2018. The beam quality was better. The statistics would be significantly larger. The same fundamental measurement, muon precession in a magnetic field, but now with the sensitivity to either confirm the Brookhaven anomaly beyond doubt or quietly dissolve it. The 2021 result hit the physics community hard. It confirmed Brookhaven. The precession rate was still higher than the standard model said it should be. The combined significance, Brookhaven and Fermilab together, climbed to 4.2 standard deviations. Not quite 5 sigma, but close enough that the language physicists used in public started shifting. Words like tantalizing and compelling appeared in press releases with unusual frequency. Theorists who had held cautious positions started openly discussing what kind of new physics could produce exactly this shift in the wobble rate. The 2023 result refined it further. More data, tighter error bars, the same stubborn deviation. Each new result from Fermilab landed in the same place, above the standard model prediction, consistently, reproducibly. What could explain it? Muons don't wobble in a vacuum. They wobble inside a quantum sea. Virtual particles constantly flicker in and out of existence around them. Electrons, positrons, photons, quarks, gluons, and every one of those fleeting interactions nudges the precession rate slightly. The standard model accounts for all of this in extraordinary mathematical detail. The calculation for the muon's anomalous magnetic moment involves thousands of Feynman diagrams and decades of work by hundreds of theorists. It is one of the most precisely computed quantities in physics. If the measured value sits above the prediction, it suggests that something is contributing to those quantum fluctuations that the standard model hasn't included. Something real, something physical, flickering around the muon and pushing its wobble rate slightly faster than the known particles can account for. New particles, a heavier force carrier, some extension of the standard model operating at energy scales that current accelerators can't directly reach, but whose effects bleed down into precision measurements like this one. Supersymmetric particles are one candidate. Supersymmetry predicts a whole mirror world of heavier partners for every known particle. The selectron, the neutralino, the muon, and those partners would contribute to muon precession loops. Leptoquarks are another option. Particles that bridge the gap between quarks and leptons in ways the standard model forbids. Dark photons, hypothetical force carriers connecting ordinary matter to a dark sector, appear in certain models that predict exactly this kind of shift. None of these have been directly detected, but the muon is sensitive to them in a way that other precision measurements are not, because its greater mass amplifies the contribution of heavier unknown particles to the wobble rate. This is the reason the muon is special for this measurement. An electron's anomalous magnetic moment has also been measured to extraordinary precision, and it agrees with the standard model. But electrons are light. Their sensitivity to heavy new physics is suppressed. Muons are 207 times heavier, which means their precession rate picks up contributions from heavier virtual particles much more strongly. If something with a mass of several hundred GeV is lurking in the quantum vacuum, the muon is a better probe than the electron by roughly a factor of the mass ratio squared. The muon is pointing at energy scales that no direct collider search has fully explored. This does not mean the answer is guaranteed. Physics has been humbled before by measurements that looked like new physics and turned out to be errors, theoretical miscalculations, or statistical fluctuations that faded with more data. The G2 anomaly is still contested, not on the experimental side, where the measurement is solid, but on the theoretical side, where a different calculation method, called lattice QCD, has produced a standard model prediction that sits closer to the measured value. If the lattice QCD number is correct, the anomaly shrinks. If the traditional data-driven prediction is correct, it persists. The theoretical community has not reached a consensus, and that uncertainty hangs over the whole enterprise. What the Fermilab experiment has done is close the door on the measurement being a fluke. The ring ran, the data accumulated, the precision tightened to 127 parts per billion, which is better than the original design specification, and the number did not move toward the standard model. It stayed where Brookhaven found it, and then some. There is something almost frustrating about how clean this situation is. An experiment of extraordinary precision, built over decades, tested across 2 different laboratories, confirmed across multiple independent runs, returning the same deviation every time. Not a dramatic deviation, not a factor of 2 disagreement, but a small, persistent, stubbornly reproducible mismatch between what the universe is doing and what the best theory in physics says it should be doing. The final combined result from Fermilab came in at a precision of 127 parts per billion, better than the original design target, and the deviation from the standard model is still there, stubbornly reproducible, pointing at something in the universe that the current theory cannot account for. If the muon G2 anomaly holds up, It means something is out there in the universe that we have never seen. Particles or forces not in the standard model. Real and physical, invisible to current detectors but leaving their fingerprints on a small wobbling magnet. That is a significant claim, and physicists know it. The history of this field is full of anomalies that arrived with fanfare and then quietly dissolved when the data got better or the theory got cleaned up. So before getting into what the anomaly might mean if it's real, it's worth understanding exactly how cautious the physics community has learned to be. Anomalies are not rare. Small deviations from predictions show up regularly. Most of them are noise. Some are systematic errors buried in the detector calibration. A few turn out to be mistakes in the theoretical calculation itself. The G2 anomaly has survived longer than most. It has been measured at 2 separate facilities, by 2 separate experimental teams, using essentially the same technique and getting the same answer. That persistence is what makes it interesting. It's also what makes the theoretical controversy around it so important. Here is what the anomaly actually says, stripped down. The standard model predicts how fast a muon should wobble when you put it inside a magnetic field. The measurement comes back slightly higher than that prediction, not dramatically higher. The gap is roughly 2.5 parts per million, but the measurement precision is now 127 parts per billion, which means the gap is real at the level of several standard deviations. In statistics, 3 sigma is considered a hint, 5 sigma is considered a discovery. The G2 deviation has been sitting between 4 and 5 sigma, depending on which theoretical prediction you use for the comparison. That last phrase is where everything gets complicated. To know whether the measurement disagrees with the standard model, you need to know what the standard model actually predicts, and calculating that prediction for the muon magnetic moment is not simple. The muon doesn't sit alone in empty space. It's constantly surrounded by a churning sea of virtual particles, particle-antiparticle pairs flickering in and out of existence, and all of them contribute tiny corrections to the wobble rate. The dominant contribution is something called hadronic vacuum polarization, which involves quarks and gluons looping through virtual states. Calculating this from first principles using quantum chromodynamics is extraordinarily hard. For decades, physicists used an indirect method, extracting this contribution from electron-positron collision data, rather than calculating it directly. That data-driven approach is what the Brookhaven result was compared against. It's what the early Fermilab results were compared against. And it's what produced the anomaly. Then, in 2023, a group called BMW, the Budapest-Marseille-Wuppertal collaboration, published a calculation using a different method, lattice QCD. This approach puts quantum chromodynamics onto a discrete spacetime grid and computes the hadronic contributions numerically from the underlying theory, rather than borrowing from experimental data. Their answer was closer to the measured value, not identical, but close enough to shrink the gap significantly. If the BMW lattice result is correct, the anomaly may not be an anomaly at all. It may be that the old data-driven theoretical prediction had errors in it, and the muon has been behaving exactly as it should the whole time. This created a genuine rift inside the theoretical physics community. 2 methods, both sophisticated, both carried out by serious researchers, giving answers that don't fully agree with each other. The data-driven approach has a long track record. The lattice approach is newer, but in principle more direct. Resolving the disagreement is now one of the central problems in this corner of physics, and it cannot be settled by doing the muon measurement again. It requires sorting out the theory. Then the CMD3 experiment entered the picture. CMD3 is a detector in Novosibirsk, Russia that studies electron-positron annihilation, and its measurements are used as one of the inputs for the data-driven theoretical prediction. In 2023, CMD3 published new results on pion production cross-sections that disagreed with earlier measurements from other experiments. Its numbers pushed the data-driven theoretical prediction closer to the measured muon G2 value, in the same direction as the BMW lattice calculation, but through a completely different path. 2 independent roads leading toward the same uncomfortable question: was the original theoretical prediction simply wrong? The physics community does not have a clean answer yet. What it has is a situation where the experimental measurement is firm and growing more precise with each analysis. while the theoretical target it is being compared against is contested. That is an unusual position. Normally, the theory is the stable side, and the experiment is the thing being refined. Here, it is almost reversed. Set that controversy aside for a moment and ask the question that matters if the anomaly survives scrutiny. What could be causing it? What kind of new physics would shift the muon's magnetic moment in the direction observed? The most discussed candidate for decades has been supersymmetry. Supersymmetric theories predict that every standard model particle has a heavier partner, a sparticle, selectrons, muons, neutralinos. If these particles exist, they would contribute additional virtual loops to the muon's magnetic moment calculation, pushing the G2 value upward. The size of the contribution depends on how heavy the sparticles are. The G2 anomaly, if real, constrains that mass range and points towards sparticles in the hundreds of GeV to low TeV range. That range has been searched at the Large Hadron Collider. No sparticles have been found. This doesn't rule supersymmetry out entirely, but it has compressed the parameter space considerably. There are other candidates, additional Higgs bosons. The standard model has one Higgs field, but extended models predict more. A second Higgs boson at the right mass would affect the muon's magnetic moment. Then there are dark photons, hypothetical force-carrying particles connected to a dark sector of matter that doesn't interact through ordinary electromagnetic or strong forces. A dark photon mixing weakly with the ordinary photon could nudge the muon's wobble rate. Leptoquarks are another option. These are hypothetical particles that couple quarks and leptons directly, something that doesn't happen in the standard model. They show up in various extensions of the theory and can produce corrections to the muon magnetic moment of the right sign and rough magnitude. None of these candidates is confirmed. All of them are speculative. What they share is that they have a kind of new physics that would leave a trace exactly where the trace has been seen. Small, precise, showing up in the wobble of a muon inside a magnetic ring. Physicists talk about this kind of evidence carefully. Something being consistent with new physics is not the same as evidence for it. The G2 anomaly is consistent with several extensions of the standard model. It is not, by itself, proof of any of them. To confirm a specific explanation, you would need to either detect the new particle directly in a collider or find the same signature appearing in multiple independent measurements in a pattern that only one theory explains. What makes physicists genuinely excited and genuinely nervous about the current moment is that the Muon G2 anomaly is not sitting alone. There are other tensions in particle physics, the proton radius puzzle, hints in B-meson decays that have come and gone, possible deviations in lepton universality tests. None of these is individually decisive. Together, they form a pattern that looks less like random noise and more like something the current theory is missing. Or they look like that until the next wave of theoretical corrections pulls one of them back into agreement and the pattern frays again. This is the genuine state of the field, not a clean discovery and not a clean null result. A measurement that refuses to go away, embedded in a theoretical controversy that has not resolved, surrounded by other tensions that may or may not be related, pointing at a region of physics that current colliders have searched and come back empty-handed from. The physicists working on this are not dramatizing the uncertainty. They are sitting inside it, running calculations, collecting more data, trying to distinguish a real crack in the standard model from an error in how the model's predictions are being computed. That work is slow and unsexy and enormously important. Either the standard model has a hole in it big enough for new physics to fall through, or the way physicists calculate quantum field theory predictions needs fundamental revision. And right now, in 2024 and 2025, the theoretical and experimental communities are not fully in agreement on which of those is true. There is a second place where muons have been quietly defying expectations, and this one involves the size of the proton. Not the proton's charge, not its spin, its size. Something that should be simple, something that should be settled, something that physicists thought they had nailed down decades ago. And then a muon walked into the measurement and the whole picture cracked. Here is what you need to know about the proton's charge radius. The proton is not a point particle. It has internal structure. It is made of quarks, held together by the strong force, and that internal structure is smeared out over a small but real volume. The charge radius is essentially a measure of how that charge is distributed across the proton's volume. Think of it as the effective size of the proton as seen by anything that interacts with it electromagnetically. For decades, physicists measured this by firing electrons at protons and watching how the electrons scattered. The angle and energy of the scattered electrons encode information about the proton's structure. Run enough of those collisions, analyze the data carefully, and you can extract the charge radius. By the mid-2000s, this had been done many times, with many different experiments, and the answer had converged on a value of about 0.88 femtometers. A femtometer is 1/400,000th of a meter. The number was small, and it was considered reliable. Physicists moved on. Then someone had an idea. What if you built a hydrogen atom but replaced the electron with a muon? This sounds exotic, but it is actually something physicists know how to do. Muons are not protons. They carry negative charge just like electrons. So a muon can orbit a proton and form a hydrogen-like atom. The difference is mass. Because a muon is 207 times heavier than an electron, it does not orbit at the same distance. Heavier particles in quantum mechanics orbit closer to the nucleus, much closer. A muon in muonic hydrogen sits roughly 200 times closer to the proton than an electron does in ordinary hydrogen. This matters enormously, because when a particle orbits that close, it is actually overlapping with the proton itself. It is sampling the proton's structure directly, spending significant time inside the proton's charge distribution. That makes muonic hydrogen an extraordinarily sensitive probe of the proton's size. Any shift in the proton's actual charge radius shows up as a shift in the energy levels of the muonic atom, and energy levels can be measured with exquisite precision using laser spectroscopy. The closer orbit amplifies the sensitivity to the proton's structure by a factor of roughly 2 million compared to regular hydrogen. A team led by Randolph Pohl published results from muonic hydrogen spectroscopy in 2010. The measurement was precise, the signal was clean, and the proton radius it returned was 0.84 femtometers. That is about 4% smaller than the electron-based value. 4% sounds like a rounding error. It was not. The statistical discrepancy between the two measurements was approximately 7 sigma. In physics, 3 sigma is considered potential evidence of something real. 5 sigma is the threshold for claiming a discovery. 7 sigma means the two measurements are essentially incompatible. You cannot blame this on random fluctuation. Something was genuinely different between the two results, and nobody knew what. This became known as the proton radius puzzle. 2 sets of experiments using 2 different types of particles, measuring the same physical quantity, arriving at numbers that did not agree. The options for explaining this were uncomfortable no matter which one you chose. Maybe there was a systematic error in one of the experimental approaches, something subtle and persistent that had gone undetected for years. Maybe quantum electrodynamics, the theory describing how charged particles interact through electromagnetism, was somehow working differently for muons than for electrons. That would be extraordinary, because QED is one of the most precisely tested theories in all of science. Or maybe, and this was the strangest possibility, the proton was actually presenting different effective sizes depending on what type of particle was probing it. Were we observing the final moments of a massive star as it collapsed before us? This was the particle physics equivalent of that question. Were we seeing a fundamental crack in the standard model, or a measurement problem? The physics community did not agree. Some groups reanalyzed the electron scattering data and argued the old value had a systematic bias pulling it high. Others stood by the electron-based measurements entirely. New electron-proton scattering experiments were designed specifically to resolve the discrepancy. Muonic helium measurements were performed to test whether the same issue showed up in heavier atoms. The Pratt experiment at Jefferson Lab, published around 2019, produced a proton radius closer to the muonic value, suggesting the older electron measurements might indeed have carried a systematic error. But not all electron-based measurements agreed with Pratt. The picture remained blurry. What made the puzzle genuinely difficult was that both types of measurements were technically sound. The muonic hydrogen spectroscopy was not sloppy work. The electron scattering data had been gathered and cross-checked across multiple facilities over multiple decades. You could not simply dismiss either side. and the theoretical machinery connecting the spectroscopic measurements to an actual radius value depended on QED calculations that themselves had to be trusted. If you doubted the QED corrections, the whole comparison collapsed. Such disagreements characteristically provoke heated argument among experimental and theoretical physicists at scientific meetings, sometimes persisting for years or even decades without clear resolution. The interplay between precision measurement and theoretical interpretation becomes magnified when the stakes involve fundamental constants of nature. Here is the deeper issue that the proton radius puzzle exposed. The muon's greater mass means it doesn't just orbit closer, it couples to the proton differently. The energy levels in muonic hydrogen are sensitive to proton structure effects that are almost completely negligible in ordinary hydrogen. This is enormously useful as a precision tool, but it also means that any tiny flaw in how QED handles muons versus electrons gets magnified by the same factor that makes muonic hydrogen so sensitive in the first place. The measurement and the theoretical framework that interprets it are inseparable. A 4% error in the proton radius, translated through the sensitivity amplification of muonic orbits, corresponds to an effect far below what would show up in any other experiment. You can only see it here, and that cuts both ways. It makes muonic hydrogen a uniquely powerful probe, but it also means there are very few cross-checks available. The puzzle pushed physicists toward a question they had been comfortable not asking. Do muons and electrons truly behave identically under QED? The standard model says yes, up to corrections from their mass difference. This assumption has a name, lepton universality. The proton radius puzzle did not prove lepton universality was broken, but it raised the possibility seriously enough that the physics community had to treat it as a live hypothesis rather than a background assumption. The proton radius puzzle never fully resolved the way physicists hoped, and it left behind a troubling question. If you measure the same object with two different types of particles and get different answers, are you measuring the same object? The standard model insists that an electron, a muon, and a tau particle are the same in every way that matters. Same charge, same interactions, just different masses. And for decades that assumption sat untested in the background of particle physics. It has a name, lepton universality. The principle is clean, and it's embedded deep in the architecture of the standard model. Nature does not play favorites among leptons. An electron couples to the weak force with a certain strength. A muon couples to the weak force with that same strength. A tau does the same. The only differences between them are the ones you'd expect from heavier particles behaving differently because of their mass, not because of anything fundamental about how they interact. If this is wrong, the standard model is not just incomplete. It is wrong about something it considers a basic symmetry of nature. That is a different kind of problem entirely. The proton radius puzzle had already planted a quiet suspicion. Muonic hydrogen and ordinary hydrogen gave different answers for the same measurement. Two tools, both well understood, pointed at different numbers. One of the possible explanations, not the most likely, but the one nobody could fully dismiss, was that muons and electrons weren't sampling the proton identically because the forces involved weren't treating them identically. That would be lepton universality breaking down. Most physicists considered that too radical, but the idea was now in the room. Then across the Atlantic from most of the theorists arguing about proton radii, a different experiment started producing results that sharpened that suspicion considerably. The LHCb detector at CERN was designed to study a class of particles called B mesons. These are short-lived particles containing a bottom quark, and they decay through the weak force into lighter particles. Crucially, they can decay into final states containing either electrons or muons. By lepton universality, the rates of those two decay pathways should be equal. Up to corrections you can calculate precisely because they come only from the mass difference between the electron and the muon. The ratio of one decay rate to the other is called RK, or RK star, depending on the specific decay channel being examined. Lepton universality predicts these ratios should be essentially 1. LHCb started measuring them. The numbers came back below 1, not by much, but consistently below 1. The 2019 and 2020 measurements of RK and RK star showed deviations at the level of 2 to 3 sigma from the standard model expectation. That is the kind of number that turns heads without quite being enough to declare a discovery. In particle physics, 5 sigma is the threshold that gets you a press conference. 3 sigma gets you a meeting room full of theorists generating explanations. The explanations arrived fast. Papers appeared within weeks proposing new particles, leptoquarks, new Z-prime bosons, various extensions of the standard model that would couple differently to muons than to electrons and naturally explain why B mesons preferred electrons over muons at the rates being observed. Some of those models also connected, at least partially, to the G2 anomaly. This was notable. 2 separate measurements, using different detectors, different particles, different methods, were both pointing toward muons behaving unexpectedly. That convergence made people take it seriously. Were we watching the same new physics from 2 different angles? Here is something worth holding in your mind about how this field works. Anomalies in particle physics appear regularly. Most of them fade. The data that produces a 3 sigma signal often produces a 1 sigma signal when you triple the dataset. Statistical fluctuations cluster in ways that look like signals. Systematic errors hide in calibrations and reveal themselves only under pressure from more data. The history of particle physics is a long list of signals that arrived with excitement and departed quietly. That is not a flaw in the method. It is the method working correctly. The whole point is to demand more evidence before accepting something new. So more data came. LHCb ran longer, calibrations improved, statistical uncertainties shrank, and in 2022, the collaboration released a new analysis with a significantly larger dataset and a substantially more careful treatment of systematic effects. The RK anomaly, which had sat stubbornly below 1 for years, moved. It moved back toward 1. The new central value was compatible with the standard model. Not a perfect match, but within uncertainties, no longer a clear deviation. The RK star measurements followed in the same direction. The B meson lepton universality signals, which had been generating theoretical papers for 3 years, largely dissolved under the weight of better statistics. This is not a failure. This is exactly what the process is supposed to look like. A hint appears, resources are directed at it, and either the hint survives increased scrutiny or it doesn't. In this case, it mostly didn't. The field moved on without having established a lepton universality violation from B meson decays. But something interesting had happened in the process of all that searching. The question of whether lepton universality actually held, whether it had ever been tested with sufficient precision across enough different processes, had moved from background assumption to active investigation. Experiments that might previously have been considered routine confirmations became precision tests of a principle that was suddenly less settled than it had looked. That shift in perspective does not disappear just because one set of measurements came back negative, and the Muon G2 anomaly did not go anywhere. That measurement, with its precision of 127 parts per billion, was still sitting above the standard model prediction. That deviation had been reproduced across multiple experimental runs at 2 different facilities across more than 2 decades of measurement. Unlike the B meson signals, it had not faded when the statistics improved. It had sharpened. Whatever was pulling the G2 value away from the prediction, it was consistent and it was specific to the muon. An electron in the same type of experiment does not show the same anomaly. The tau is too short-lived to measure this precisely. It is the muon specifically that sits in the disagreement. That specificity is the thing that connects these 2 threads. Whether the B meson decays showed what they appeared to show or not, the broader question remains live. Are muons genuinely equivalent to electrons in every interaction, or is there something in the dynamics of the weak force, or some undiscovered coupling to an unknown field that treats them differently? Lepton universality has not been broken, but it has been examined more carefully than ever before, and the examination has not been entirely reassuring. The LHCb results came back closer to the standard model as the dataset grew, but the question they raised did not disappear, because the Muon G2 anomaly was still sitting there, and together they pointed at the same uncomfortable possibility, that muons might not be the perfect copies of electrons that the standard model says they are. The particle that nobody ordered in 1936 may be the particle that physics needs most in the next 50 years. That is not a small claim. The history of particle physics is built on machines that get bigger, heavier, more expensive with each generation. The Large Hadron Collider at CERN is 27 kilometers around. It took decades to design and build, cost roughly $10 billion. It collides protons at energies that would have seemed impossible to an earlier generation of physicists. And yet, for all of that, there is a fundamental limitation built into every proton collider that no amount of money or engineering can fully solve. Protons are not fundamental. They are made of quarks, held together by gluons. When two protons collide at high energy, you don't get a clean interaction between two point-like objects. You get a mess. Quarks collide with quarks, gluons radiate everywhere, secondary particles spray in all directions. Only a fraction of the collision energy actually goes into the physics you care about. The rest is noise. This is the problem muons solve. A muon is a point particle. No internal structure, no quarks, nothing hiding inside. When two muons collide head-on, every bit of that energy goes directly into the collision. The interaction is clean, sharp, and far more efficient than anything a proton collider can produce. At the same nominal beam energy, a muon collider delivers dramatically more usable physics. Put another way, a muon collider operating at 10 TeV of center of mass energy would outperform the LHC in ways that matter enormously for finding new particles and testing the edges of the standard model. For the kinds of searches that physicists most want to do right now, probing the scales relevant to the G2 anomaly, studying the Higgs boson with precision, hunting for whatever is leaving 5 fingerprints on the muon's magnetic moment, a muon collider would be the right tool, possibly the only tool powerful enough to actually get there. There is a catch. The same property that makes muons so valuable as collider particles is also the engineering nightmare sitting at the center of this entire project. Muons decay, not slowly, not over the course of a useful experimental lifetime. They decay in 2.2 microseconds on average in their rest frame. You cannot store them, accumulate them quietly, then collide them at leisure the way you can with protons. The moment you produce muons, the clock starts. You have to collect them, focus them into a beam, accelerate them to collision energy, actually collide them, all before the beam disappears into a shower of electrons and neutrinos. This requires acceleration rates that are far beyond what conventional accelerator technology was designed to handle. It is not impossible. It is just extraordinarily hard. Here is how the process would have to work. First, you need to produce muons in large quantities. The standard approach is to fire a high-energy proton beam into a target, producing pions. Then capture the pions as they decay into muons. This gives you a muon beam, but not a useful one yet. The muons come out moving in slightly different directions with slightly different energies, spread out in what physicists call phase space. A spread-out beam won't focus into a tight collision point. You have to cool it. And cooling a muon beam is not like cooling anything in ordinary experience. The technique being developed is called ionization cooling. The muons pass through a material, lose energy through ionization interactions. Then that energy is immediately replaced only in the forward direction by radio frequency accelerating cavities. Repeat this enough times, and the beam gets tighter, more focused, more parallel. The problem is, you have to accomplish this cooling in a tiny fraction of a muon lifetime. This was because the beam is always decaying. Ionization cooling is real. It has been demonstrated in the lab, but scaling it up to the level a full muon collider remains an open engineering challenge that an international collaboration is actively working through right now. After cooling comes acceleration. The muons need to reach collision energy faster than conventional accelerators typically run. The designs under consideration involve rapid cycling synchrotrons and linear accelerators working in sequence. The muons to 10 TeV or beyond in the time available before the beam decays. At those energies, time dilation helps significantly. A muon moving at 99.9998% of the speed of light has its lifetime stretched by a factor of thousands in the lab frame. Engineers far more time to work with than the rest frame lifetime suggests. The same relativistic effect that allowed cosmic muons to survive their journey through the atmosphere becomes an engineering resource inside the accelerator. Then there is the problem of what to do with the decay products. Muons that don't make it to the collision point decay into electrons and neutrinos. The neutrinos mostly pass through everything harmlessly. But at the energies a muon collider would operate, the neutrino flux from beam decay would be significant enough to require careful management of where the beam is aimed and how the machine is oriented. This is a radiation safety consideration that doesn't exist for proton colliders and has to be designed around from the beginning. The physics payoff for solving all of these problems would be remarkable. A high-energy muon collider could produce Higgs bosons directly, through muon antimuon annihilation into a Higgs, at a rate and with a precision that the LHC cannot match. The LHC produces Higgs bosons as a byproduct of messy proton collisions. A muon collider tuned to the Higgs mass would produce them resonantly, the way a guitar string rings when you hit exactly the right frequency. The measurement precision this would enable for Higgs properties is orders of magnitude beyond what is currently possible. And for whatever is causing the G2 anomaly, whatever new particle or force is nudging the muon's magnetic moment away from the standard model prediction, a 10 TeV muon collider would be operating at energy scales where those new physics effects would become directly visible, not just inferred from a wobbling spin. The Muon Collider collaboration is a real, active international effort with physicists from dozens of institutions working on the accelerator physics, the detector design, the cooling technology, the theoretical case for why this machine is worth building. No government has committed funding for a full Muon Collider yet. It remains in the design and feasibility phase, but the seriousness with which it is being pursued has grown substantially over the past several years. The physics case has only gotten stronger as the G2 anomaly has persisted, and the questions surrounding lepton universality have deepened. The muon started as an accident, a track in a cloud chamber that curved the wrong amount, a particle that had no place in any theory, a thing that Rabi famously noted nobody had asked for. 9 decades later, that same particle is the centerpiece of the most ambitious accelerator concept in high-energy physics. The same 2.2 microsecond lifetime that made muons a paradox in the upper atmosphere, the decay rate that required relativity to explain, is the primary engineering challenge standing between the present and a machine that could rewrite particle physics. Step back from the experiments and the numbers and look at what the muon actually is in the story of physics. And the picture that forms is a strange one. It was not predicted. It was not needed. When Carl Anderson pulled its track out of a cloud chamber in 1936, the reaction from the physics community was not excitement about a confirmation. It was something closer to bewilderment. The electron already existed. The proton already existed. Nobody had drawn up a blueprint for the universe and left a blank space labeled, heavier copy of the electron, unstable. Insert here. The muon arrived uninvited and has refused to leave quietly ever since. Think about what this particle has actually done to physics across the decades. It survived a journey that classical mechanics said was impossible, arriving at the surface of the Earth in numbers that only make sense if Einstein was right about time. That wasn't a minor confirmation. The muon's survival is one of the cleanest, most visceral demonstrations of special relativity that nature provides. Not a thought experiment, not a mathematical abstraction, but a real particle doing something that contradicts every intuition you have about how time works. Every single muon that registers in a detector at sea level got there by living longer than it should have. The universe bent time to deliver it. Then the muon went further. It sat inside muonic hydrogen and told physicists the proton was a different size than they thought. It wobbled in a magnetic field at Fermilab and produced a number that the standard model cannot fully account for. It showed up in beam-Eason decay experiments and briefly suggested that it wasn't behaving the same way as electrons, which the standard model insists it should. One by one, in different labs, on different continents, with different methods, the muon kept coming back with answers that didn't quite fit the picture physics had drawn of the universe. This is the kind of particle that gets theorists out of bed at 3 in the morning. Not because it's flashy, because it's specific. The G2 anomaly isn't a vague signal buried in noise. It's a clean, reproducible measurement with a precision of 127 parts per billion that still doesn't match the prediction. That is not a rounding error. That is a gap. And gaps like that are where new physics lives. The implications of this gap deserve emphasis. A discrepancy at this level of precision cannot be dismissed as experimental error or instrumental artifact. The measurements come from independent collaborations using entirely different methodologies. The Fermilab collaboration confirmed what Brookhaven had found. The theoretical calculations have been refined by thousands of hours of computational work and cross-checked by multiple independent teams. When measurement and theory diverge this sharply at this level of precision, it is not the measurement or the theory that is wrong. Something is simply missing from the theoretical framework. Something real enough to shift the numbers at a scale of 1 part per billion. The muon is not lying. Here is something worth sitting with. The standard model describes the muon perfectly in terms of its properties: mass, charge, spin, decay products. The theory gets all of it right. What a standard model cannot do is explain why the muon exists as a separate thing from the electron at all. It describes the muon the way a catalogue describes an item: name, weight, specifications. But it does not tell you why the item is there. Nature appears to have built matter in 3 copies, 3 generations, each one heavier than the last. First generation: up quark, down quark, electron, electron neutrino. That's enough to build everything you can see: atoms, molecules, stars, planets. All of it runs on first generation particles. The second generation, charm quark, strange quark, muon, muon neutrino, is just heavier versions of the same recipe. The third generation, top quark, bottom quark, tau, tau neutrino, heavier still. Nothing in ordinary matter requires them. They appear briefly in high energy collisions, and then they decay back into first generation particles. The universe made 3 drafts of itself, and only kept using the first one. Nobody knows why. That is not false modesty. That is the actual state of the field. Physicists have names for all the particles. They can calculate their interactions with extraordinary precision. But the reason nature chose 3 generations, the reason the masses fall where they do, the reason the pattern repeats, none of that has a satisfying answer inside the standard model. The model describes the structure without explaining it, like finding a building with 3 identical floors and no architect's notes. It is a description of what is observed, not an explanation of why nature constructed things this way. The standard model is extraordinarily successful at predicting experimental results, but success at prediction is not the same as understanding. Understanding would mean knowing what principle, what symmetry, what deeper organizing logic led to the 3-generation structure in the first place. The muon sits at the center of this puzzle. It is the most accessible 2nd-generation particle, lighter than the tau, longer lived than anything containing charm or strange quarks, produced in enormous numbers by cosmic rays every second without needing an accelerator. When physicists want to look for cracks in the standard model, they keep coming back to the muon because it is both sensitive and available. Its greater mass compared to the electron makes it more responsive to effects from heavier unknown particles, particles that might explain the 3-generation structure, or supersymmetric partners, or whatever is actually out there beyond the current theory. If something exists that the standard model doesn't account for, the muon is one of the most likely places to see its fingerprints. And that is exactly what the G2 experiment keeps finding: a fingerprint, small, persistent, refusing to go away across multiple experiments, multiple labs, multiple years of data. The proposed Muon Collider is the logical next step in this conversation. Proton colliders, like the Large Hadron Collider, smash composite particles together. The actual collisions are messy, with energy distributed across quarks and gluons in ways that require enormous statistical effort to untangle. A Muon Collider smashes point particles together, clean collisions, direct interactions, far less noise in the data. At 10 TeV, a Muon Collider would probe energy scales well beyond what the LHC can reach for certain processes, and it could produce Higgs bosons in a direct, controlled way that current machines cannot match. The challenge is the 2.2 microsecond lifetime. You have to produce muons, cool them into a tight beam, accelerate them to high energy, and collide them before they decay. And you have to do all of that faster than physics allows you to be careless. The same short lifetime that made muons a paradox in the atmosphere is the engineering problem standing between the present and the most powerful particle collider ever built. Strange that the particle's most inconvenient feature, the decay rate that required relativity to explain, that stumped physicists for years, is now the central obstacle in building the machine that might finally explain the particle itself. Consider the distance these muons travel before you ever see them. Cosmic rays arrive from distant galaxies, from supernovae, from some of the most violent events in the universe. They hit the upper atmosphere 15 kilometers above your head and produce pions, which decay into muons, which then survive long enough, through time dilation, through the bending of time itself, to reach the ground and pass through your body. Right now, multiple times per minute, particles produced by the death of stars light years away are moving through you at nearly the speed of light, and most of them you will never know about. That is not a metaphor. That is a physical fact about what is happening to you at this moment. And those particles produced in the fringes of galaxies we will never visit, raining down as a byproduct of events we can barely imagine, are the same particles that have been quietly telling us the standard model is incomplete. The same particles that humans figured out how to trap in rings, measure with extraordinary precision, and use to image the interior of ancient pyramids. The same particle that Irabi said nobody ordered, that Anderson stumbled onto in a cloud chamber, that confused the entire field of physics for a decade before anyone understood what it was. That is the arc of the muon, discovered by accident, misidentified immediately, used to prove relativity, deployed to look inside mountains, measured with ever greater precision until the measurements started coming back strange. And now sitting at the center of the biggest open question in fundamental physics: what is out there beyond the standard model? And why does the universe need 3 generations of matter to do something 1 generation could have handled? The muon was never supposed to be there. It was never supposed to survive long enough to reach the ground. And it was never supposed to disagree with the best theory in physics. And yet here it is, doing all 3. And still nobody fully understands why.